Today we're going to talk about how to calculate enthalpy and entropy changes in chemical reactions. When we calculate the change in enthalpy, which remember, enthalpy is just a fancy word for heat, so delta H is the symbol for that change in enthalpy, we can use this reaction equation that the change in heat is equal to the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. Now, what are heats of formation? Heats of formation are these are the enthalpy changes that are involved when a compound is formed from its elements. So when you have an element itself in its free state, natural state, and this includes diatomic elements, the heat of formation is going to be 0 for those. And they're usually on AP tests, etc., they're not going to tell you the values for those. They expect you to know that the heat of formation of an element is going to be 0. So we want to watch out for that. Now, where do we find the rest of these values? I'm going to show you this once, and from then on, I'm just going to simply call out values, realizing that we always get them from this our table like this. Now, this is the one that we use in class, and it has values, as you can see across the top, it has values for the heats of formation of substances. Those are in kilojoules per mole, and this is going to be very important here in a few minutes. Whereas when you look at the entropy values for substances, those are in joules per mole Kelvin. So depending on whether you're finding the entropy change or the enthalpy change will determine which of these two columns that you're going to use. Another very important thing, look over here at water. Notice that it makes a very big difference whether you're dealing with liquid water or gaseous water. If you're dealing with liquid water, your values for both the heat of formation and the entropy value are different from those of a gas. So you have to be very careful that you're paying attention to what state of matter those substances are in. So this is a 2-page document, and you're going to use this document to find all of your heats of formation. So you might have this handy so that you can look at it while I'm talking about the values that we're going to be using in these calculations. So the first example here says to calculate the enthalpy change for the reaction, determine whether it's endothermic or exothermic. That's going to be determined by the sign of the value at the end. And then determine whether it's thermodynamically favored or thermodynamically unfavored. Remember from a previous set of notes that we talked about how when we're dealing with enthalpy, the lower the enthalpy, those negative values, those exothermic reactions are considered to be thermodynamically favored. If it's a positive value for delta H, it's going to be thermodynamically unfavored. So positive, unfavored, negative, favored when we're talking about our enthalpy. So let's look at the values. I've already showed you the paper where I'm going to get these values from, so you can look at the paper if you want to. When I look up the value for CH4 for delta, the heats of formation, delta H, I get negative 74.8. Remember, oxygen is 0, no matter what I multiply it by, and you would be multiplying by the coefficient, it's going to still be 0. For water, it's negative 285.8, but there are 2 of the water molecules, so we're going to multiply that by 2. And carbon monoxide is negative 110.5. I'm not putting the units with them. They just become cumbersome in this kind of an equation calculation. So we'll put them in at the end, realizing that they're going to be in kilojoules per mole reaction. So the heat of reaction then, I usually abbreviate this and simply say sum of products minus the sum of the reactants. That's going to be 2 times the negative 285.8 plus our negative 110.5. There's our products. I'll make those kind of more like brackets to kind of keep it separated. So we'll do that. So 2 times negative 285.8 plus negative 110.5 minus, and this is where people always make their mistake, we're going to subtract the quantity inside these parentheses. Since the value for oxygen is 0, it's simply going to be negative 74.8 for our CH4. So be careful that you pay attention to those signs when you plug them into your calculator. When we do this calculation, we end up with a negative 571.6 plus a negative 110.5. And we're going to be subtracting off again the negative 74.8. And we end up with negative 607.3 kilojoules per mole. And they like the units because you could balance this differently. You could, for instance, double this, balancing up here to get rid of that 3/2. So in order to show that this is for this specific equation and no other, we're going to put per mole reaction. That's the way they're showing it now. So that's the value for our delta H. Now notice the sign is negative. Since the sign is negative, that means it's going to be exothermic. That's just by definition. As soon as it got that negative sign, it became an exothermic reaction. And since it is an exothermic reaction, it is thermodynamically favored. I know it's a heck of a word to write, but thermodynamically favored. So based on our calculations then, and this is part of the answer that needs to be boxed in, based on our calculations then, we've got this reaction being thermodynamically favored as far as enthalpy is concerned. Let's do the same reaction now. We can do the same type of equation, but this time we're going to use the entropy values from the table, and we're going to calculate the change in entropy for this system. Again, same exact equation. We're looking at the sum of the products minus the sum of the reactants. We're just going to be looking up a different column. So if you look for CH4 under the delta S column, we get, or under the S column, the entropy column, we get 186.2. We get, now this is for entropy. According to thermodynamics, the only thing that has a 0 value for entropy is a perfect crystal at 0 kelvins. And this is not a perfect crystal at 0 kelvins. So this will have a value now when we're talking about its entropy. And that value is 205. Keep in mind that we now need to multiply that by 3/2, multiply by the coefficient. Water in the liquid state is 69.91. We will need to multiply that by 2, and carbon monoxide is 197.6. So getting our value for delta S, we're going to take products minus reactants again. So we're going to have our 2 times our 69.91 plus our 197.6. Again, I should put those more in brackets. And now we're going to subtract the quantity, 186.2 plus 3/2 times our 205. When we calculate out this first set of brackets, we get 337.42. And we're going to subtract off then from the other brackets 493.7. Much better to get the total on those brackets first before you do anything else, because otherwise you're going to accidentally subtract the 186.2 but add the 3/2 times the 205. So you'd be much better off to get these values like this first. So when I subtract these off, I end up with a change in entropy of negative 156.2. Remember, the units for this are different, joules per mole Kelvin. Now, what does that mean for entropy when we have a negative value? Well, for entropy, a negative value means that we have an unfavored reaction. Entropy is unfavored when it's negative. We always want, remember, lazy slobs, low energy, high entropy. So this is entropically unfavored. I'll spit it out here in a minute. Entropically unfavored. We cannot say whether it is exothermic or endothermic. That makes no sense with entropy. The therm part, the exothermic and endothermic, are only for our um, enthalpy calculations. So this is really all we need to put when it comes to our calculation of delta S. It's entropically unfavored. So now what does that mean? Well, it means we have a reaction that is favored as far as enthalpy is concerned, we can see up here from our calculation, but unfavored as far as entropy is concerned. So how can we tell whether this reaction is actually going to occur in nature? And it's pretty cool that just with calculations on paper, we can make that determination using these entropy and enthalpy values. Again, both of these act together to determine whether the reaction is going to occur or not, but they don't always work together. A reaction that has a negative delta H and a positive delta S will always be thermodynamically favored. We sometimes call these spontaneous reactions because they work. I'm just going to put works out here, okay? A reaction that has a positive delta H and a negative delta S, unfavorable in both situations, will always be thermodynamically unfavored, meaning it is non-spontaneous or it won't work. But when we have situations where delta S and delta H have the same signs, either they're both negative or both positive, then we've got to do a further calculation because we can't tell just by these two values whether this particular reaction is going to work or not. We need to calculate something called the free energy, or delta G, the change in free energy, in order to determine whether this is actually going to be a favored spontaneous reaction or not. Gibbs free energy, as it says here, is the maximum amount of energy that can be coupled to another process to do useful work. In other words, the total energy available to the reaction system. It depends on the size and the direction of the enthalpy and entropy changes. Are they negative, positive? How big are they? Now, if we get a negative value for our free energy, meaning free energy is given off by the system, then it's called an exergonic reaction. It's just a new term. Nicely, it still it uses the X and N prefixes to help us out a little bit. Endergonic reactions are the ones that are unfavored, and we can tell those when we see that positive delta G. Guys, delta G is the be-all and end-all of whether these reactions will work or not. If delta G is negative, the reaction 100% will work. If delta G is positive, 100% won't work. So how do we calculate this? Well, the official equation is that delta G is equal to delta H minus T delta S. I have to admit that I always write it like this. Delta G is equal to delta H minus delta S T, because it looks like ghost, and I have always called this the ghost equation. So it doesn't matter which way you write it. I don't care. I will probably write it as the ghost equation and refer to it as such. So notice also that the temperature is in kelvins, and that's going to make a difference to us if they happen to give it to us in something other than Kelvin, like they did on this one. Now, all of these entropy and enthalpy calculation values were done at 25 degrees Celsius. So if we don't use 25 degrees Celsius, we really can't do what we just did and calculate from scratch. They would have to give us other values. But since all of our values were done at 25 degrees Celsius and it's asking us whether this reaction is spontaneous at that temperature, we can do this. So let's look at this first reaction, or at this reaction again. We've already determined what the delta H and delta S values are. We said that delta H was negative 607.3 kilojoules per mole. That's important. And that delta S was negative 156.2 joules per Kelvin mole. Now, I'm going to do something right now before I get myself into some big trouble later in the equation. As soon as I know those two values, I am going to get those in the same units, because if I don't, I'm going to forget later, and the equation is not going to make any sense. It's going to be incorrect. So I'm going to go ahead and change delta S. I always change delta S, and I'm going to change it to kilojoules instead of joules. And to change it to a bigger unit, I need to make the number smaller. So I'm going to change this to negative 0.1562 kilojoules per Kelvin mole. And that's what I'm going to use in the calculation. So we've already established that delta G is equal to delta H minus delta ST, if I want to use the ghost form of the equation. Delta H, as we just said, was negative 607.3 kilojoules per mole. And we're going to subtract off delta S, which we said was negative 156.2. No, I'm sorry, we just changed that. See what I mean? How easy that is to do? So be careful. 0.1562 kilojoules per Kelvin mole. We're going to get rid of that Kelvin in this expression because we're going to multiply that by the Kelvin temperature. Now remember, to get Kelvin, we're going to add 290, it's going to be 298, but we're going to add 273 to the Celsius value to get our Kelvin value. So we're going to end up with 298 kelvins for our temperature here. When we do this calculation, then we end up with negative 561 kilojoules per mole reaction. And what does that tell us? That tells us that this is an exergonic reaction because it's negative. And as soon as we determine that that is a negative value, exergonic, we know that it is thermodynamically favored. So that's how we calculate on paper whether a reaction will actually occur in real life or not. Pretty cool.